a brief exercise in how small an atom is. And I know you guys have done like how much a mole is and all this stuff, right? You know, if you had a mole of boogers, you'd have to have, I'm just kidding. But anyway, here's a meter. This is 10 to the 1th meters, yeah, isn't it? Or 10 to the 0 meters, yeah? 10 to the minus 1 meters is this much. We can see that, can't we? 10 to the minus 2 is a centimeter. We can see that with the bare eye, can't we? Naked eye. My eye is naked, okay? And a millimeter is 10 to the minus 3rd. Can't we see that? That's easy. Millimeters we can see. You can see them from where you are, okay? I believe if we got close to this with our bare eye, we could see something that is 1/10 of a millimeter, don't you think? Yes. So I'm just going to say, let's just for the sake of having a lot of fun here, the 10 to the minus 4th is 1/10 of a millimeter. That's the smallest thing. Let's split that, let's make that big. Okay, so let's take the smallest thing we can see and make it as big as a soccer field. Are you picturing this? Not a football field, a soccer field. Okay, now it is a soccer field long, and a soccer field has 100 meters in it, from goal line to goal line. Every 100 meters has 100 centimeters. And if you take a sheet of paper, if you take the normal paper we have in our copiers, this is a little known fact, 100 sheets of that is a centimeter. This is how I count stacks of paper. How many copies do I have for skill sets, right? Because like there they are. How many do I have? I don't sit there and count them. I just measure them. Okay, every millimeter is 10, right? Okay, so we can measure this, right? So this is 100 centimeters. Every centimeter is 100 sheets of paper. So here's what I'm saying, is that if we take the smallest thing our eyes can see, let's suddenly make it ginormous, 100 meters tall, which is like on the order of kind of the biggest thing we can look at, right? And stack paper 100 meters tall. Are you picturing this? Are you picturing this? Are you with me? Yes, every sheet of paper is an atom. Did that confuse you?
Yeah. So one sheet of paper.
Every sheet of paper is an atom. Take the smallest thing you can see, make it as big as a soccer field, stack paper that high. Every sheet of paper is an atom. It's small, isn't that small?
That's really small.
But it's not inconceivably small, which is sort of an interesting thing. It's not inconceivably small, it's just really small. Yeah? Thank you for burning up your brain in this small mental exercise. Now, what? No, straight up and down, straight up and down. Stack them straight up and down. 100 meters high. Take the soccer field. On end, yes, on end. There we go. This is good. Okay, now, here are the problems. Here are the problems, and we're going to later bore into the nature of these problems. Okay? But here are the problems with this thing. What he says is, look, you've got an electron. The electron orbits the nucleus. This is like, remember those gravity problems that we solved where the force of gravity equaled centripetal force, and we solved for the period of orbit and all this fun stuff, right? He says, look, this can work the same way. They're gonna, this thing's attracted to that. That can cause the centripetal force, right? Okay, and this thing is going to orbit. Well, here's the problem. Here's the problem. Okay, this there are two problems. The main problem, though, is that as this electron moves from here to here, doesn't the electric field out here change? Yeah. If I'm looking at the electric field, it's changing. Isn't a changing electric field how you make an electromagnetic wave? Yes. Remember the antenna? Positive, negative, positive, negative. This is how you broadcast. This thing is going to broadcast some frequency of light. Yes? It's going to broadcast some frequency of light. Light contains energy, yes? Yeah. And therefore the energy must come from this. And it's going to be unstable. It's going to decay and slam into the nucleus in a fraction of a second. A millionth of a second, all matter will decay. Is that a problem? Yeah, matter is unstable and decays within a millionth of a second or something like that, right? Okay, yeah, so that's problem number one, not, you know, basically Rutherford just answered that with, well, it doesn't. Okay, which is the real answer. I don't know why it doesn't, but it doesn't, right? Okay, and then the second problem is that these things can be any distance that they want from the nucleus, yet they knew at the time, there was an idea that they couldn't be just any distance because of spectral lines, right? This would say that if you excite the atoms, it can put out any color it wants because there can be any orbit you want. But they knew that there was some sort of a thing there where you could only be certain distances from it. There was a growing feeling that. So this did not explain those spectral lines at all that we could see. And if you're going to explain something about atoms, you better explain spectral lines because they're really exciting. Actually, we don't know why they are, right? Back then they didn't, right? Okay, so those are the problems. But before we bore further into atomic theory, let's solve closest approach problems. And these are rather mundane. problems that you could have solved at the end of chapter 17, but unfortunately you've forgotten all of chapter 17, and so there we have it, right? Okay, but here is the notion: is that this alpha particle is going to fly. It's flying along, and its kinetic energy, it's 1/2 mv squared, right? And you could put this in your little notes. These things are in your. Oh, did I give you your note guide? No. I know. That is so sad. Where are they? Who's booing me? Here, hand these out. A boogala? Boogala isn't even a mole, right? A mole is 10 to the 23rd, right? Boogala is 10 to the 14th. A mole is the number of atoms such that they have a mass equal to their atomic weight. Yeah. Boogala! All right. Last. If I could have your attention, you are just on the verge. I was just on the verge of solving a closest approach problem. You guys are like on the edge of your seat. And you're like, and what next? Okay. So here it is. You've got an alpha particle. It's got all that kinetic energy. It's like flying along, right? Okay. And there's the nucleus, and it's repelling it. And so basically, what you say, at closest approach, it hits it head on, and it actually comes to a halt. Right? So all the kinetic energy is turned into electrical potential energy, right? So that is equal to V times Q. Well, Q, this Q here is the alpha. Okay, so that's 2e because it's the alpha particle. Why is it 2 electron charges? 2 protons. There we go, right? Protons have the same charge as an electron. Okay. So it's got 2 electron charges like that, and then what do we do with our V? Well, remember the voltage, the nucleus of the atom is like a point charge, and the voltage near a point charge is K Q over R. What's that Q? Charge of the other one, of the nucleus, right? Okay, so this is the nucleus. Right, this is our closest approach. So when they say, what's the distance of closest approach? And if you forgot, this guy is 9 E9 Newton meters squared per Coulomb squared. God help us. So basically, kinetic energy turns into electrical potential. There's a formula really similar to this. It just says 1 FMV squared is EV, right? This one basically is 2 EV, right? Or something like that, because it's an alpha particle, right? So to solve that first question, what is the closest approach of an alpha particle going that speed as it approaches a carbon nucleus head on? We can just set this up, right? We've got 1/2 mv squared, right, is going to be K. What's the charge of a carbon atom? 6e. Yeah, carbon's element number 6, right? Okay, so it's 6e, right, over R, right? And then this is times 2e. Is that right? Yeah, so it's KQ over R. And then my preference is, obviously we could just stuff in the numbers that we know right now and solve for R. But my preference is to take this thing and solve it for R. So that's what I are going to do. Okay, so this is 12ke squared over 1/2 mv squared. I guess we put the 1/2, we could put the 2 up there, couldn't we? No. Don't want to do that. I'm not going to do it. That'd be too much. That's asking too, you're asking too much of them. Okay, so this is going to be 12 times 99, right? 1.602 e minus 19th squared, right? Divided by 1/2. And then this is our alpha, so what is it? 6.644. Should have been my clue when you asked if those were 4s or 9s.